we will move on with the high-level API for the matrix multiplication mode and its usage. So first we start again with importing the plotting stuff here and the nice widgets we have seen before, and also NumPy and the torch, the PyTorch and the XXTorch packages here. So HXTorch is an extension to PyTorch, and PyTorch is a very well-known machine learning framework, and all the internals you've seen in the previous notebook are encapsulated in HXTorch. So you so it provides a very sleek interface for this matrix multiplication mode. So we can look at the so to say central operation of this HXTorch extension. This is the matmul operation, and it is for multiplication of two matrices. And we can take a look at the function signature here. So we have an input matrix, we have a weight matrix, and we have some additional, this is the same as in the PyTorch framework, and we have additional hardware parameters we can discover or discuss later. And before you can use this function, you have to initialize your hardware connection and to load calibration, and this is all encapsulated in this HXTorch init function here. So when we execute this, it allocates the hardware and it loads the latest nightly calibration from disk for the specific setup. And you can also pin calibration here and load a specific calibration, but we will not do this. And then you are ready to use this matrix multiplication mode. So you can just type HXTorch matmul from, I will use here full matrices. So maybe I start with a matrix with a shape of 100 and a value of 12, and I multiply this with a matrix that has also a shape of 100 and maybe let's say 10 and a value of 20, and we can look at the result. Something seems wrong here. I'm not sure what happened. I missed here. Okay, live coding. And as you see here, it works out. So we expect in the end 10 times the same value, and it kind of looks that. So we are using here the analog multiplication on the setup in the lab. And since this is analog circuitry, it's not always the same, but our main calibrator, you have heard before today, did a great job here. So it's mainly around here, 55, the output. And as you already see here, we multiplied 100 times 12 with 20 and summed it up, and the result is not as high as you expected it. So when I changed this for the PyTorch interface, I got much larger numbers. But this is because all these numbers are in the units of the ADCs we are using. So we have the synapses, the digital to analog converter, and they have a certain unit, and also the rates and the synapse rates are in a certain unit, and also the analog to digital converter in the end that reads out the neurons. So you have to what happened here? HXTorch is not defined. Yeah, thank you. Okay. And so what happens here is we take a PyTorch tensor here, and it's float units, And what happens internally is some pre-processing. So it's converted to unsigned 5-bit integers for the input, and signed 6 or 6-bit plus sign weight matrices. So we have here 7-bit numbers. So it's from -63 to 63. And then it's petitioned on the hardware, and then it's executed on the brain scales to ASIC via Ethernet in the lab. And then the results is read back again and converted back to the same types, the same. So it's flowed again in the end and returned as a PyTorch tensor. And the very nice thing about this operation is that, in contrast to the spiking mode, we can multiplex this operation. So when we have a larger matrix we want to multiply, we can multiplex this in time, or we can even use several different brain scales to ASICs. So when we want to let's say we want to multiply this larger matrix here, and the actual hardware array is only the smaller part here in the upper left, and we can partition these larger matrices into smaller ones, and we can calculate all the parts on their own and then add them up in the end. And so it's very easy to apply this method to larger networks in the end. Yes, since we are using an analog system, we have to deal with some noise and fixed pattern deviation. So as you have seen here before, we have when I repeatedly execute this, you can maybe see that there is, for example, this is calibrated very good. Okay, so sometimes there is one neuron that has always a bigger number, or always returns a bigger number, and we can look at this here in a very nice way. So I've set up here a plot of this for you, so we can execute this cell here. And what we do here is we, as before, multiply a constant input with a constant weight, and we expect all the outputs to be constant. And this is kind of what we see here. So here is the output on the left, or on the y-axis, and the x-axis you see the different neurons on the chip. And the reason why this is here somehow orientated oddly is that this orientation here, so neuron 0 in the middle and neuron 256 here on the left, on the right, is because this is the spatial setup on the ASIC. So the synapse driver are in the middle of the synapse array here, and the neurons are oriented this way. And we can play here around with the different sliders. So when we can increase the input value, and the output should increase as well. And we can increase the weight value, and the output should also increase. And you can even choose a negative weight, and you get negative outputs here. And as you can see already, we have these fixed pattern deviations, so to say. So we have some of the neurons are always a bit higher than others, but it may be more pronounced on your setup. I've got a very nice one here. The other parameters, we have also the row number. So this is only a multiplication in one row of the ASIC, and we have 128, at least in the upper half of the chip, and we can change this as well, and you will see that the output slightly changes. And this is because every synapse driver is a bit different, although we apply the calibration. Okay, yeah, I hope you can still see my screen here. I have a bit of connection issues at the moment. Sorry. Yeah, but you can. This is why you can try this at your own, so you can get a very nice experience. Although this is on hardware and a shared resource, at least on my screen, it's very fluent. Yes, the first parameter here is the number of sands, so we can, and this encodes so we can send the same input multiple times to hardware. And this way we can increase the charge that ends out on the neuron in the end. So this is a way to scale somehow the input value. So yeah, doubling this number should also double the output, at least to some extent. Yes, we can also take a look in the next slide on the linearity of the operation. So we have a weight. We choose a weight matrix here that goes from -63 to 63, and we multiply. We use a constant input here to multiply this with. And the result we can see here. So we have again here the output, and here is the neuron number, so to say, but also the weight, because the weight is increasing with the neurons. And yes, you can see here this nice linear relationship between the weight and the output. And we can again here increase the number of sands. So it will, we expect it to be steeper here. And yes, it is. And we can also change the row number and the input values. And there is a lot more to explore here, and get some more details about the operation, how it behaves. So, for example, here in the upper picture, you can really go to the limits to the hardware. So you can, for example, increase the weight value to its maximum. Maybe we decrease the number of sands to, so we cannot, we can see something. And then you can decrease the input value. And for very low input values, it depends a bit on the actual ASIC. And it does not work for me, but it may be for you. So on some of the ASICs, you can see that in the middle here, you get a bit larger outputs. And this is because the pulses are sent from the middle of the ASIC, and they receive here a larger input. Yes. Are there any questions regarding this matrix multiplication? I don't see any comments on the Mattermost chat, so I think you're fine with this. In the end, we will also be around some time in the Zoom and also in the Mattermost channel, and the Jupyter Hub will still be up, so you can investigate this further in the end if you like. And I have some possible questions for you here down here. So then let us continue with the interesting part, I think. So we have seen here a lot of hardware fixed pattern deviations. But it's not a problem for us, because we want to use this as to accelerate machine learning and deep neural networks in the end. And as we are able to train on the hardware using the hardware, our models are in most cases able to adapt to these deviation and learn them. So we have a model that knows about the hardware, so to say, in the end. So this number 5 Yin Yang in the loop called Jupyter Notebook shows an usage example of the training with HX Torch. First, we import all the important stuff again. Training with hardware in a loop means that double clicking is not a good idea, that we calculate the forward path on the brain scales 2 ASIC, as we have seen before, and the backward path of the learning operation is calculated on the host computer, on the CPU or GPU. So what we are using here is the normal backpropagation scheme. So we have a forward operation, and we calculate the whole machine, the whole network, the whole model, and then we have a backward path that is calculated entirely on the CPU. And for this, we need a model for the, so we need to know what happens on the hardware, so to calculate the gradient in the end on the CPU. So for this, we need a mathematical model, and we are going with a very simple linear approximation. So you see here, this first part here of the equation is the normal multiply accumulate operation. So we have an input vector x and a weight matrix y, w, and an output vector here. And there are additional constants here. So these g, we call it gain factor. This is essentially the conversion between the different ADC and DCA units. So the units of the input, the rate, and the output. And we have additional noise from the neurons from the analog readout, and this we assume to be normal distributed with a sigma standard deviation here. And when you call this HX torch init function, these two numbers are measured for you on the hardware, and we can take a look at them. So the gain factor on my setup at least is 0.002 something, and the noise is about 1 here. And these numbers are used to calculate the backward path when training the hardware. And since we have this model here, we can also, when there is no ASIC around, or there are a lot of people on the setups like today, we can also use this model to simulate also the forward path on the CPU. So we somehow simulate the hardware to some extent. And this we call mock mode. So we mock the hardware away, but yeah, you get also nevertheless numbers from your operations. So you can see here the difference between these two. So we have also in the mock mode, we have this noise here, this normal distributed noise on the neurons, but we have no fixed pattern deviation. So here you can see we have a lot of, especially in the end here, fixed pattern deviations between the different neurons and rows, and this is all hidden here, so it's not implemented in the mock mode. And also in the end, we have here larger deviations, and especially here down here, it's a bit off linear, but this is also not implemented in mock mode, and the mock mode just clips our values at the end, so at 127 here in this case. So it is linear to the end, and then it clips the value. But it allows us to somehow test our models, how they respond to noise and to this limited ranges here. Yes, you can use this mock mode via this parameter mock equals true here in every call to hxtorch functions. And you can read about the hxtorch frontend in our paper, and also the implementation of the mock mode and the layer initialization we are using later, and the backward pass implementation in my master thesis I finished last year. Today we are going to use a small data set for training. This is called a Yin Yang Data Set, and I will execute this cell. So this basically is a class that provides some samples, and why it's called Yin Yang we can look here. So first we define some colors to plot and the class names. And when we plot this data set, it looks like this. So it has a yin-yangish shape. And all these dots here correspond to one sample in the data set. So we have every sample has a x and a y coordinate, and all these dots correspond to one sample in the data set. And the color decodes its class. So we have 3 classes here. We have first the yin class in black, and the yang class in white, and in orange the dot. So we can also look at one specific sample here. I missed the S. Okay. So we have here the x coordinate, the y coordinate, and the complement of the two. So the first one is 1 minus the x component, and this is 1 minus the y component. And yeah, this data set is presented in more detail in this archive preprint by Laura Kriener. You can take a look at this, and there are also benchmarks and proposals for, and you can also use this network to train spiking neural networks, but we will stick with normal deep neural networks today. Yes. Are there any questions? No, there are no questions. So yeah. And here we define first helper functions to get a nice color map in the end, so nice pictures. And the first function here is combined test and training method. So what is done here? We prepare a test set. So what is the network in the end will be tested for grids in the whole value range of the network. So it goes from 0 to 1 in each coordinate, and so we can display the network response later. And what we do here is we prepare this test data, and we merge it to the training data to have this in a single call to the matmul operation, because we have a lot of overhead today because of this Ethernet connection and the scheduling and so on. So it will be a bit slower if we haven't done this, but we are not training on the test data set. You can check my code here. The training is implemented here. So here in the lower half we have the training loop. So we are looping over the epochs, and we are calling this function here, and we are increasing the step of the scheduler and the optimizer in the end, and also plot a nice picture of the network response to the input grid here. Yes, so here is the actual model I came up with for this tutorial today. So the model looks, if you're using PyTorch normally, this model looks very similar to you, I think. So we have also here linear layer, and we have a rectify linear unit, but this is what this one is here converting. So it's a bit special. And this is because we have the output of the matrix multiplication is in 8-bit integers, and the input is 5-bit integers. So we have to somehow, adapt for this and convert it. So it's basically shifted. So it's just bit shifting. We're losing resolution, so to say. But we have the 8-bit output resolution is a bit ambitious. So we have, due to the noise, it's not really the solution, the resolution we can get from the hardware. So what we do here, we have a linear layer and a layer with 128 hidden neurons, rectify linear unit, non-linearity, and an output layer with 3 classes. And this average parameter here is we are, since we have this noise on the hardware, we average over 5 neurons in the end to get more stable results. Yes. So first we instantiate this model with using the mock mode. So all what comes next is simulated only. So at least the next 3 cells, and we can here ensure ourselves that it's mock mode by printing. This is the model, so you can see here it's mock mode true. And you can see here the number of cents is set for you. So this is somehow magic. HX Torch knows how much input you need, how much number of cents you need to get reasonable output from the neurons. So you do not have to take care of that yourself. Now we are introducing some learning parameters. So we have we are using a batch size of 350 here, learning rate, and a learning parameters decay here. So after each epochs or after each batch, it's the same in this example here. So every epoch in our case here is 1 batch, and so it's the same. We are reducing this learning rate by this factor here. And this loader loads the data set. So we are using here the size of the batch size. And this data set is modified in a way that every time you use this data set, the samples are redrawn from a random distribution. So you can see this here, samples 0 again. If you when we call this multiple times, oh no, this is not the case here. Okay, maybe it's because I use I defined a fixed before, but in the end during learning it's the case. Yes. Oh, it should be. Let me check. So with a loader dot data set, and then 0 for the first. This is the same. Oh no, it's not. So now it's not. It's, every access to the data sets shuffles again the output. But yeah, basically that's it. And these called the train function trains this model now for 200 epochs here, and you can see that it trains the network, and in the end you should end with a nice shaped here yin yang like shape. And yeah, I think it's really nice to look at this learning here. And I hope you will all end up with these kind of yin-yang shape here. And after this, we can try to move this network here to the actual BrainScales 2 hardware. So what we do here, we instantiate another model with mock mode set to false, and we load the states, so all the weights from the previous model that we pre-trained in the mock mode. And this is done in this cell. And now we can also set up the training parameters here. So we use a larger learning rate and then a smaller learning rate here because we have already trained the model for some epochs, and a larger gamma to adapt to the differences between the hardware and the mock mode. And we can train this, and as you see here, it's a bit slower. And it sometimes looks very odd, and this is because, as I mentioned before, we have the differences between the mock mode and hardware mode. So in some sense, it's a good approximation, and in others, it's not. So depending on the calibration, it may work in first place for you, or it may not. So it looks at least decent for me here. If it's not the case for you, you can repeatedly call this cell here. And what this does is it trains for another 15 epochs, so you can continue training. And if this does not work out, you can also go with a different model that is trained in the simulation. So maybe this model is a solution that is not optimal for the hardware. So we can again call this. Let me just wait for this to finish here. We can call all the cells above another time. So you have to start with this initialization of the model again and train for another epoch, and then it should work in the end. And if you experience any issues, you can, you're free to ask us. So please say something when it looks odd, and we can take a look at it. You are free to modify this model and even optimize it further. And you can also check on the special feature of this, or the nature of this data set. So it's not possible to classify this with a linear classifier. So when we remove these the hidden layer and we go with only the last layer, we can, for example, see here that now it's really it takes some time, but it is not able to distinguish or to see the single dots here to that problem. Yes, this was the whole walkthrough to our prepared tutorials, tutorial notebooks here. We will be around for some time here in the Zoom and also in the MetaMost chat to answer your questions. And you are free to play around with all these notebooks. And if you want access in the future to our hardware, it's you can always contact us, and we will make it happen. Thank you for attention.